There is a direction in space that sounds easy and turns out to be almost forbidden. Not Mars, not Jupiter, not Pluto. Straight up, out of the flat plane where the planets orbit, toward the space directly above the Sun. It feels obvious. Point a rocket upward and leave. But orbital mechanics is not built around what feels obvious. It is built around velocity, and every spacecraft launched from Earth begins with a problem it did not choose. Earth is already moving around the Sun at about 30 kilometers per second, more than 67,000 miles per hour. A probe launched from Earth inherits that sideways speed before its engines do anything. For missions to Mars or the outer planets, that inherited motion is a gift. The spacecraft is already traveling in the same broad plane as its destination. But if the goal is to climb above or below that plane, the gift becomes a trap. To go nearly straight up, a spacecraft must fight the sideways orbital motion it already carries. It cannot ignore it. Without canceling or redirecting that speed, the craft does not escape vertically. It remains in a tilted orbit around the Sun, still swept along by the same momentum as Earth. That is why reaching a point above the Sun's pole can require more energy than reaching worlds billions of miles away. Distance is not the enemy. Direction is. This is one of the hidden prisons of the solar system. The planets move through a thin disk called the ecliptic. Most asteroids, probes, and spacecraft stay close to that same plane. We have explored outward across the disk with remarkable success, but we have barely explored above it. And that missing direction matters. The Sun is the closest star to Earth, yet for most of human history, we have watched it from the side. Telescopes can track flares, loops, sunspots, and eruptions in extraordinary detail, but they mostly see the solar equator. It is like trying to understand Earth's weather while never leaving the tropics. The poles of the Sun are not quiet edges of a sphere. They are tied to the solar magnetic field, the 11-year solar cycle, and the streams of charged particles that fill interplanetary space. Fast solar wind flows from polar coronal holes. The Sun's magnetic field reverses through processes connected to these regions. Space weather that can disturb satellites, power grids, navigation, and astronaut safety begins with physics we have mostly viewed at an angle. One mission found a way into this hidden territory. Ulysses, launched in 1990 by ESA and NASA, did not fly straight upward from Earth. It first traveled to Jupiter. The giant planet's gravity bent the spacecraft out of the ecliptic and sent it looping over the Sun's poles. Ulysses measured solar wind and magnetic fields from latitudes no previous probe had reached, but it could not truly show us the polar sun. Its instruments belonged to another era, and it carried no modern cameras for direct polar imaging. The first direct views came much later. Solar Orbiter, led by ESA with NASA participation, launched in 2020 and gradually tilted its orbit using repeated Venus flybys. In March 2025, it captured the first direct images of the Sun's south pole. The view revealed a tangled magnetic region, far stranger than the smooth cap we might have imagined from Earth. That should feel startling. We had photographed Pluto close up, driven rovers across Mars, and dropped the Huygens probe through Titan's atmosphere before we truly began to see the poles of our own star. But the polar sun is only part of the prize. Above the ecliptic, a spacecraft could help us understand the shape of the entire solar system. The Sun is surrounded by a magnetic bubble called the heliosphere, carved by the solar wind as it pushes into interstellar space. Inside this bubble live the planets, comets, dust, and every spacecraft humans have launched. Outside, it is the galactic environment between stars. For decades, textbooks often showed the heliosphere like a comet, a rounded nose and a long tail. Newer models suggest something stranger, perhaps more like a deflated croissant with two curved lobes instead of one long wake. The problem is that we live inside the bubble. We are trying to map the shape of our home from within its walls. Voyager 1 and Voyager 2 crossed the heliopause, but they crossed it near the planetary plane. Their data is historic, yet it is still only two narrow paths through a vast three-dimensional structure. A spacecraft escaping. High above the ecliptic could sample the heliosphere from a completely different angle and look back at the solar system as a structure in the galaxy. That is the view we do not have. The planets as a flat ring, the dust as a faint glowing sheet, and the heliosphere wrapped around everything in its true shape. So how do we get there? A larger rocket alone is not enough. The problem is not simply altitude. It is the need to redirect a spacecraft that begins life moving sideways at planetary speed. The best solutions feel backwards. One is the solar Oberth maneuver. Instead of climbing away from the Sun, the spacecraft first falls toward it. Solar gravity accelerates the probe inward until, near perihelion, it is moving incredibly fast. At that exact moment, it fires its engine. The timing matters. A rocket burn performed at high speed, deep in a gravitational well, adds far more orbital energy than the same burn in quiet space. The Sun becomes an amplifier. The dive becomes the launch pad. A mission like this would be extreme. The spacecraft would need a heat shield, precise navigation, and an engine burn timed near its closest solar approach. But if it worked, it could fling the probe onto a steep path out of the ecliptic, turning a fall toward the Sun into a climb above it. Another solution is slower: solar sailing. A solar sail is a huge reflective sheet pushed by sunlight. The force is tiny, but it never runs out. Near the Sun, photon pressure grows stronger. Over months or years, a sail can gradually tilt a spacecraft's orbit higher and higher, trading patience for propellant. The most powerful future mission may combine both ideas: use gravity assists or a sail to move inward, dive close to the Sun, perform a high-energy maneuver, then rise into a polar escape path. To go up, the spacecraft first goes down. If it succeeds, the science would be remarkable. Near the solar poles, it would pass through fast solar wind, often 700 to 800 kilometers per second, steadier and thinner than the turbulent wind near the equator. It could measure how that wind forms, how it changes with the solar cycle, and how it feeds the heliosphere. It could watch the Sun's magnetic field from the angle where the global pattern finally makes sense. Better polar measurements could improve forecasts of future solar cycles and help protect the technology civilization depends on. Farther out, the same probe could become a heliosphere explorer, measuring cosmic rays, energetic particles, and the boundary between solar space and interstellar space from a direction no spacecraft has sampled well. There is also a quieter reward: darkness. The ecliptic plane is dusty. Comets shed material. Asteroids collide. Tiny grains scatter sunlight and create the zodiacal light, the faint triangular glow visible from dark places before sunrise or after sunset. Beautiful as it is, that dust is noise for astronomy. A telescope far above the plane would rise out of much of the haze. It could search for faint signals around other stars, study the cosmic background with less contamination, and look at the galaxy from a cleaner platform than anything near Earth. That is why the space directly above and below the Sun is not empty. It is a missing perspective on our star, our protective bubble, and the architecture of the solar system itself. Exploration is not always about going farther. Sometimes the frontier is a direction we have avoided because physics made it expensive. Sometimes the most important photograph is not another close-up of a distant world, but the first overhead portrait of the place we already live. Above the Sun, there may be no surface to land on. What waits there is a view, the polar face of our star, the real shape of the heliosphere, the dusty planetary disk below, and the solar system finally seen from outside its own flat plane. It is one of the most important images humanity has never taken. And to capture it, a spacecraft may have to perform the strangest escape imaginable, falling almost into the Sun before it can finally climb above it.